All right, now we're looking at the set 2 AP Physics C Mechanics free response questions. As usual, if there's any corrections, I'll put it in the pinned comment below. All right, a small sled slides across a rough horizontal table with initial velocity v0. The coefficient of kinetic friction between the sled and the table is mu k. The string connects the sled to a device on the ground. The device maintains a constant tension Ft in the string by unwinding the string as the sled moves to the right. The total mass of the sled is m. The string attached to the device at x equals 0, height of y, as shown in figure 1. Horizontal position of the sled is represented by x, as shown in figure 2. Express all answers in terms of m, mu, k, ft, x, and y as appropriate. Okay, cool. So the y is the height. Now the x and the y are changing. And the dot below, draw and label forces that are exerted on the sled a short time after t0, but before the sled has come to rest. Each force. So sometime between here, between here and here. Okay, so like maybe before it comes to a rest here. So, unwinding the string as the sled moves to the right. Okay, so when he's like this, if I look at this guy right here, I'm just gonna look. I always do like, well, I have mg. What's touching it? I got a normal force. Because of the normal force, do I have friction? I do have friction. It's going to the left because it's sliding right. And then the tension is down into the right, like down into the left because it's pulling. So I would expect mg. I would expect a normal force. I would expect a frictional force to the left. And I would expect a Ft tension down into the left like that. Okay, yep. Determine the expression for the angle theta the string makes with the vertical and the sled has traveled a horizontal distance. All right, so distance x. And we want to put things in terms of these variables here. Can I emphasize how important it is to just use those variables? This is a triangle we look at, right? This is a triangle here. This is y, this is x, and I know tangent of theta is equal to opposite over adjacent, it's x over y. So tangent of theta would equal x over y. So theta would be inverse tangent of x over y. Okay. Derive an expression for the normal force exerted on the sled as the table as a function of position here. All right, so I'm going to grab this thing. And I think it's helpful to do the free body diagram and decompose because we're going to do net force equals ma. So I'm going to decompose the Ft into components like this. This is Ft cosine theta. This is Ft sine theta. And this is theta. Oh, is that theta? Oh, let me double check. Theta is the angle here. So it's the angle with respect to the vertical. Oh, no, this is theta, right? Like in terms of theta, let me make sure I get that right. The angle looks like this. Yeah, this here angle is theta. With the vertical is theta. So I messed that up. With the vertical should be theta. So I should redraw the triangle maybe a little bit differently. I'm going to draw it more like, because I know this is theta, I'm actually going to decompose it this way instead. So this is Ft cosine theta. This is Ft sine theta, right? Okay, so now let's do F net equals ma in both the x and the y direction. The x direction, let's say left is positive, and we'll say up is positive, okay? So in the x direction, we have force of friction to the left. We have Ft sine theta to the left, and that equals ma. Those are the only forces to the left. And then vertically, in the y direction, I have Fn up, I have Ft cosine theta down, and I have mg going down. And that has to equal 0, because the vertical acceleration is 0. It's only accelerating horizontally. So here I'm going to get Fn is equal to Ft cosine theta plus mg. Now, I got to figure out what cosine theta is, because I'm not allowed to use theta in my answer, right? So if this is theta, what is cosine of theta? It's adjacent over hypotenuse. What's the hypotenuse? Just Pythagorean theorem, right? So therefore, cosine of theta has to be the adjacent over the hypotenuse, like that. So I'm going to change this to equals Ft. This scrolling up and down is annoying. Okay, y over square root of y over square root of x squared plus y squared plus mg. That is the normal force here. Okay, The ft is constant, y, and these are the variables I'm allowed to use. I'm allowed to use ft, x, y, m and stuff like that. Okay. Derive an expression for the next horizontal force is right here, is force of friction plus ft sine theta. The force of friction is mu Fn, mu k Fn. And then ft, here I got to do the sine theta, so let's redraw the triangle right here. Maybe I'll just get a picture of the triangle so you guys can see what I'm doing. No, okay. It looks like this. This is x, this is y, this is theta, this is square root of x squared plus y squared. So when I want sine of theta, it's going to be opposite over hypotenuse. So it's x over root x squared plus y squared. And then this is the mu k, and I just multiply by this thing here. ft plus, ft not plus, ft times y over square root of x squared plus y squared plus mg plus ft x over square root of x squared plus y squared. Oops, I don't need parentheses there. That is the net force. I would not simplify any more than that. You can if you want, but yeah. Derive an expression for the work done by the string as the sled moves from 0 to L. Okay, so we're going from 0 to L, and it's doing negative work. It's going opposite direction because it's going to the right, but the force is going to the left. And what I want to do is the work done on the string. So I want to do integral of f dx. I'm going to make this negative integral. Why is it negative? Because the work is negative. Because it's moving to the right, but the component of the tension for to the left is to the left, and so that's slowing it down. And they only want the tension force. So this would be ft, and it's the component that is parallel to, so it's ft sine theta. It's the one that's parallel to the direction of motion, sine theta dx. So that's why that negative sign is there. It's because the work has to be negative. And ft is constant. The sine of theta, we said, was x over root x squared plus y squared dx. And we're going to integrate this from 0 to L. So that is the amount of work. Okay. The sled comes to rest after traveling a distance x equals 2L. As the system slides from 0 to L, the energy dissipated by friction is E1. As the sled slides from L to 2L, the energy dissipated by friction is E2. Is E1 greater than or less than or equal to E2? So what do we care about? So work is the change in energy. So we care about the work done by friction. The work done by friction is equal to the force of friction times the displacement. In both cases, the displacement is the same. We're going from 0 to L. That's a displacement of L. And here's a displacement of L. So really what I want to compare is whether the force of friction is any different. Well, let's look at the force of friction equation. Force of friction, that's equal to mu k times Fn. Mu k is constant. How about Fn? Let's look at our expression for Fn. Fn is here, like this, right? Now as x increases, the Fn is going to decrease, right? Because the denominator, like y is constant, mg is constant. As x increases, Fn goes down. So we say like, as x increases, Fn decreases, right? Therefore, so this one is going to go down. Therefore, the force of friction is going to go down. So as you move further to the right, the normal force is going to decrease, right? That means the frictional force will decrease. That means the work will be. So what is the end? E1 is more energy lost, and by that justification I just explained, during E1, the Fn is greater than during E2. That's because smaller x means larger Fn, which means larger force of friction over the same distance, distance, L. Thus, the work is greater. Work done by friction is greater. Okay. All right. let's look at the second one. Block M1 of mass, block 1 of mass M1 is held at rest while compressing an ideal spring at amount delta X. The spring constant of the spring is K. Block 2 is a mass M2, where M2 is less than M1. At time t equals 0, block 1 is released. At time tc, the spring is no longer compressed. Block 1 immediately collides and sticks to block 2. The blocks stick together, and the two-block system moves with constant speed v as shown. Frictional effects are negligible. One thing I'm noticing about this, by the way, is set 2 is very similar to set 1, just slightly different adjustment. The impulse on block 1 from the spring during the time from 0 to t is Js. The impulse on block 1 from block 2 during the collision is J2. Which of the following expressions compare the magnitudes of Js and J2? Actually, this one's different. So this is the impulse from the spring during the interval, and here's the impulse on block 1 from block 2 during the collision with J2. Which of the following? Okay, so the impulse, right, is Ft, and that causes a change in momentum. That's what you want to be thinking about here. Okay, so Js, all right, the impulse from the spring, this caused the block to go from 0 to v. We'll call it v1, speed, maximum speed of the block, speed of block 1. But however, afterwards for the J2, it caused the block to slow down, right? But not as much. V1 to V. So this is a smaller delta V, right? Because V1 minus V is definitely smaller. So, or V minus V1, whatever. The difference here, because this went from 0 to V1, this one V1 to V, which is not 0, right? So this is a smaller delta V. And so this one has to be a smaller impulse. So J2 is smaller. So this one is where J2 is smaller. On the following axis, draw the graphs of the magnitude of the momentum of each block as a function of time. Before and after TC, the collision occurs in a negligible amount of time. The grid on each graphs are drawn to the same scale. So the momentum, so the block, when it's doing the spring, is pushing out. He is, as a function of time, I gotta think about that one. He is not gaining momentum linearly. Like his acceleration is steepest at the beginning when the spring is compressed, because the force of the spring is doing more. But as the spring is stretched out, the force of the spring goes down. So his acceleration is going to go down. So I actually would expect it not to be a straight line, but it kind of curves up like this. Okay? And it should kind of have like a zero slope right here, because right when it's fully stretched out, did they say at TC it's fully stretched out? At time TC, the spring is no longer compressed. Okay, so right at TC, the spring is no longer compressed. That means the force on the thing should be 0, so it should curve up, and it should have like a horizontal tangent line right at that point. Now it's going to collide, and which block is bigger? So they say M1 is the bigger block. So they're going to move off together, right, with the same speed, but M1 is bigger, so M1 is going to have more momentum, and M2 is going to have less momentum. But they should have the same total momentum. So I would expect M1 to drop like that, and M2 was sitting at rest the whole time, then it collided, and then it gained momentum like that. So a couple things to note is that this one should be larger than this side, and the sum of these two heights should equal this original height. That's by conservation of momentum during that collision. And so this one is a bit trickier, I think, than set 1, because you have to understand this is a curved graph, and that has to do with the fact that the spring is not providing constant force the whole time. It's only providing it's a kx, it's a linear, it's proportional to the displacement, so the spring force reduces as it moves on, not a straight, it just goes up like that. Okay. Show that the velocity of the two-block system after the collision is given by this. Okay, so first we want to figure out how fast the spring is moving, the block is moving here, and that you would do conservation of energy. 1/2 kx squared is equal to 1/2 m v1 squared, right? Because that's where the spring potential energy is getting converted into kinetic energy of this guy. So v1 would be square root of k over mx squared, which you could write as root k over m times x, or delta x if you want. And then looks like they're using delta x. I'm just going to keep it as x there. And then we do momentum conservation, right? This guy's moving at v1. And then they both move off together with a v. So then you would say m1 v1 is equal to m1 plus m2v. But you know what v1 is. It's equal to that guy. Or you could solve for v. It's m1 v1 over m1 plus m2. And that's m1 over m1 plus m2. Instead of v1, I just write it as root k over, oh, this is m1 here of these guys, right? m1 times x. Okay. Now, what they did here is they simplified a little bit because they brought the m1 inside. So they made this square root of k m1 squared over m1, right, over m1 plus m2 x. They brought the m1 inside and they canceled one of those. So that's how they got that. I don't think it's necessary to do that, but you can just to make it look like what they got there, right, this one here. Group of students use a set to perform an experiment. They measure the block 1 to be mass of m1 is 0.5 and the spring constant to be 150 newtons per meter. The mass of block 2 is unknown. They perform several trials. Each trial, the springs compress a different distance delta x, and the final velocity of the two-block system is measured. Then they graph that. They want to draw a line of best fit. And then let me mess with this. Trying to make it look pretty good. Okay, that's pretty decent. You guys had a ruler on a piece of paper. It probably would have been easier. Okay, and then that's the line of best fit. Use a best fit line to calculate the mass of block 2. Now, I want to keep in mind we have this equation here, right? This is V is equal to, all right, let me just grab that equation here. So, yeah, let's just grab their equation that they have here, the one that they gave. Let's just talk about this one. So then this guy is the y value, right, on the graph. This is the x value, so that means this has to be the slope. That's why they drew it this way. So we want to calculate the slope, and then we'll set it equal, and then we'll solve for one of them. We'll solve for it. Let's find the slope. Okay, pick 2 points. I'm gonna pick. What do I want to pick? I'd like to pick points that are easy to read, but I can't see anything easy to read. So I'm gonna pick this point here, and then I'm gonna pick, say, I don't know, this point right here. We'll just imagine that those 2 points are good. So this guy's point, 525, and this is comma point, I don't know, 55, and this is the point 0.15. No, not 15, 175, because this is 15 right here. So this is a 175, and this is be 0.2. So the slope is about equal to 0.55 minus 0.2 over 0.525 minus 0.175, and I don't know what the units of this are going to be. I would have to think about it for a while. I don't think it's necessarily measured. Oh, I get a slope of 1. Is that right? Is it about 1? Let me see. 0.01. No, I must have done something wrong. 0.35. Oh, it's 0.525. That's why. It's 0.525. Oh. So I always like to check to make sure, especially I get a weird number like that. I was like, I wasn't expecting it to be 1. I think it's about 10, right? So that's what I got, about a 10. And that's equal to root k m1 over m1 plus m2. I'm going to just solve what they want us to figure out. They want to figure out to calculate the mass of block 2. So I'm going to find m2. So you're going to multiply this out. Then divide by 10 and subtract. Okay. So in this case, oh, oops, shoot. They told us K was 150. They told this was 0.5. Is that what they said? 0.5? Yeah, 0.5 kilograms right here. And then, so divided by 10 minus 0.5. We get M2 is equal to 0.366. Okay. After the experiment, students use a balance to measure the block of mass M2 and find it to be greater than what was determined in part D. So M2 goes up. To explain this discrepancy, one of the students proposed that the spring constant was incorrectly measured. The students measure the spring constant again and record the value of K prime. Should they expect that K prime? So if M2 is really larger and find it to be greater than, we want to know how's that dependence on K2. So I might solve for K in this one, or solve for K in this case. So our data is still 10. It's 10 equals, and let's just rearrange. It's root KM1 over M1 plus M2. You could probably reason it from here. If M2 goes up and it has to equal 10, then K had to go up also, right? So that means the K prime should have been bigger, and that would have resulted in a bigger, sorry, I want to make sure. So the spring constant was incorrectly measured at the beginning of the experiment. So if they measured it too small, then M2 would be too small. Find it to be great. Oh, no, I'm trying to reason out in my head real quick. I'm going to straighten in my head the order of what's happening. Okay. They find M2 to actually be greater than what was determined. Okay. So our calculation for M2, let's just kind of work it out. Our M2 calculation was this, right? It was root KM1 over 10 minus M1. So this one, when I actually measured, it's bigger than I expected it to be. So if this was bigger than I expected this to be, then what that means is, like, the value I calculated was too small. And if it was too small, it's because the K I used was clearly too small. So the K I must have used, so the K I used was too small. So the real K should be bigger. Okay. And I think I wrote that out, but somehow the logic was confusing me. So if K is bigger, then the M2 would the calculation for M2 would be bigger, which is what I need because the M2 was too small. So I need a bigger calculation for M2, which means I need a bigger calculation for K, or I need a bigger K value to get a bigger calculated M2 value. Okay, that's cool. I'm not going to write it out. So a bigger K value needed to calculate a larger M2 value to match the experiment, the measured data, measured mass. Okay, so we have a uniform board of length L and mass M attached to the pivot L over 4 on the left end of the board. Left end of the board is attached to ideal spring of spring constant K is attached to the ground. The right end of the board is initially held by students, so the spring is unstretched, as shown in Figure 1. The student slowly lowers it and releases the board. The board remains at rest in the horizontal position, with the spring stretched, as shown in Figure 2. The rotational inertia of the board about the pivot is I. Okay, and the rectangle below, which represents the board, draw and label the forces, not components, that act on the board, while the board spring system is in equilibrium. Each force should be represented by an arrow that starts on and points away from the board and should represent the location. Okay, so the act on the board while this is in equilibrium. So it's this is the unstretched, and then it's released, and then it comes down to here, and this is the equilibrium position. Okay, so equilibrium position is Figure 2. Yes. Okay. Let's just do gravity first. Wait, is it negligible mass? Nope, it has mass. So it acts at the center, so we got mass there. mg. We got a spring here. The spring is stretched. It's pulling down. And then the axle is holding it up. And let's say the axle is right here. It's the axial force. Yeah, it's L over 4. So it should be like there. Anything else touching it? That's it. Nothing else is touching the system. Right? Okay. Derive an expression for the distance the spring stretches when the board is in equilibrium. Express your answers in terms of KLM. Okay, so we just do net. We'll do net torque equals 0. And the way you're going to do this is you're going to say this is my axis of rotation there. And you're going to say the torque from mg and the spring force should match. Now, because the axial force is locating at L over 4, and this distance here is L over 4. This distance to the center of the board is L over 4. Why is I know at the center? It's because it's a uniform board. So the center of mass is right at the center. Those are both L over 4. So let's say let me grab a picture of this and just so I can draw on it instead of, I don't want to mess up with that answer here. So then I would say, okay, so let's say counterclockwise is the positive direction. Clockwise is the negative direction. So then I would say the spring force times L over 4, because this distance is L over 4 from there to there. From there to there is L over 4. And then the mg causes a counterclockwise rotation. That's mg times L over 4. That's equal to 0. So here you just find the spring force has to equal mg. And that's k delta x has to equal mg. And so they want to find delta x is mg over k. And I can use k, I can use m, I can use physical constants. So that's fine. Student pushes the board down on the right side, stretching the spring a new distance delta x2. Okay. From the end stretch position, the board is held at a small angle theta 0 with the horizontal shown. The student then releases the board from rest. At time t equals 0, the board is released. Time t equals 1, the board first crosses the horizontal. Sketch a graph from the magnitude of the angular acceleration of the board as a function. So he releases the board from rest. So this hand is not here. So the only torque. So we have this k at delta x, and then we have gravity still acting here. But so what happens is the net torque will be 0 when it's horizontal, right? Because it will be balanced, like we said. So I expect that, the angular acceleration here ought to be 0. But as it moves, right? So like it has the most angular acceleration here at the start because it stretched the most. So then what happens as a function of time, okay, is that it decreases. So like it initially has an angular speed, but then and it gains an angular speed, but then the displacement kind of decreases. So the question I'm asking myself is, how does this go down to 0? Does it do a concave down? Does it do a concave up? I would say that initially it moves pretty far. So I want to think about what the solution ought to look like. Maybe the way I could prove this is I could do net torque equals I alpha. The net torque being the k delta x, right, minus mg equals I alpha. Delta x I can think of as delta x is r delta theta, right? Because the distance the linear angle motion, I could say approximately like that. This is just to give me a rough idea of what's happening. So this would be k r delta theta minus mg equals I, and this would be the second derivative of theta dt squared, right? The second derivative of this. So does that help me think about what's happening? This thing, the second derivative being positive means the acceleration is, I'm still trying to reason out whether it should go down like this. I think it should be more gradual, because I think the acceleration, does it die off really fast? Because it will speed up as it dies off. So I really want to think about, okay, so you guys aren't expected to know how to solve this differential equation. So there's no way that we could use that, I don't think. Well, maybe. It's a second order, but it's supposed to be some kind of sine or cosine. Never mind. It's supposed to be sine or cosine because it's going to do harmonic motion. So what am I going to think about here is I could think about the energy, but how does it affect the angular acceleration? So what's the angular speed going to do? Is it going to be getting faster and faster? Or is it going to be getting slower and slower? Let me think about this for a minute. I think because it's going to gain the maximum speed as it goes up, because it takes time to accelerate, it's actually going to do this. But I am not 100% sure on that one. That's what I'm going to put down for my answer. I think it's going to concave down like this, because in the beginning it doesn't move very much, so I don't expect the acceleration to change very much at the early time. But as it picks up speed, I would expect it to change its position a lot more, which would cause the spring to then start dying off a lot faster. I don't think they necessarily, you'll get scored on the reasoning, just sort of whether or not you can generally get an intuition for that shape. I bet as long as you had those points, you might, there might be a point related to the shape of the curve. Derive an expression for alpha 0 of the board immediately after the board is released. So this one I kind of already did. I was saying that, you have your net torque equals I alpha, or alpha 0 in this case. The net torque would be K delta X minus mg from our free body, or K delta X, oops, I forgot the R. So that's L over 4 minus mg L over 4 is equal to I alpha 0. And then this is K delta X. Oh, this is delta X2, right? That's how much we stretched it. Yeah, I think I just divide by I. So I could factor out an L over 4 K delta X2 minus mg divided by I is equal to alpha 0. And that would be fine. I think that would be... Am I allowed to use anything weird? I think that's it. That part was pretty easy. 2 blocks of equal mass are attached to the board, equal distances as shown in the point. The board is pushed down the right side of the spring, stretches the same distance delta x2 as part C. The board is then released. How does the new angular acceleration when the blocks are attached compare to the original angular acceleration? Well, the net torque is different now, right? So what's going to happen? Oh, actually, I think it'll be the same because you push it the same distance. So the spring force is the same. The gravity never changed. But now you have these two guys right here. These are the new things, right? mg and mg. But they're equidistant. And I only care about the component. Oh, I messed up on this last one. The mg, look, I'm just making all kinds of mistakes here. So I didn't actually draw. This is me being sloppy and lazy. Okay, it was lazy of me to do that. Okay, lazy of me to just not draw the free body diagram. I teach you guys to draw the free body diagram so much, and then I was just lazy here when I did this. The torque is related to the theta. It's related to the angle, and that's because the r vector from the axis of rotation, they are not perpendicular to each other, right? And so I know that like this angle is theta 0. So I can take the component of the r that is perpendicular to the spring force. That would be L over 4 cosine theta 0. And this would also be L over 4 cosine theta 0. So I'm missing a cosine theta 0 up here. L cosine theta 0. Okay, I caught myself when we were doing this problem. Because as I was drawing the free body diagram, I was like, oh, no. Those things are there. Okay, so now that I've done that, these two mg's will balance out their net torque, right? So the net torque's not going to change, so the angular acceleration is going to be the same, right? Because basically the two added masses have exert equal and opposite torques. Oh, nope, I have that wrong. Okay, I'm being really sloppy on this one, so I apologize. This one was a lot trickier than I realized. Okay, so if I do them as mg, here's the tricky thing about mg, is that it's not, what's changed is if I include the mg, the net torque is the same, but by including the m as part of the system, by making mg, I've included the masses as part of the system, so the I increases actually, because I've included 2 extra masses here. So if you're going to do it that way with the mg's for each of the blocks, then you have to say like the mg, if including the block as a system, blocks in the system, they add a force mg, but their net torque is 0. Net additional torque is 0. If the net additional torque is 0, then what's going to happen is that so then you have net torque equals I alpha. So the spring force and the gravitational force didn't change. So no change on the net torque, But because we're including those masses now, this went up, increased. Thus, the angular acceleration must decrease. Increased because there is now more mass in the system. And that causes a reduction in the angular acceleration of the system. So I would say the new angular acceleration is smaller. That's a little bit tricky there. Now, why is it that I can't just do the system of the board? That would be more complicated, because if you do the system of the board, let me just kind of illustrate why that matters. If you're doing the board, then it's not mg is exerted here. It's a normal force from the block. And how would you calculate the normal force from that block? Is that the two forces would have, well, like, sorry, not Fn1. Of the blocks themselves, it would be the normal force, Fn1, and then mg. And then on the other guy, it would be Fn and mg. Sorry, at an angle like that. But they have different accelerations. This guy's accelerating downward, this guy's accelerating upward. So the normal forces exerted on the two blocks are different. So the normal forces that they exert on the rod themselves, on the board, is actually different between the two because of the net acceleration that's happening on these blocks. Thus, you can't just talk about the mg like that. If I do an mg approach, I have to include, I'm basically saying I'm including those blocks in the system. But if I'm including those blocks in the system, the I necessarily has to increase. So this one was a tricky question. I got to go look back at set 1 if I made a mistake on this part similarly. But I don't think so, because this one was about adding masses. So the other one was a little bit different. Okay.